All right. Ryan, you want to get started?
Yeah, I'm good.
Easier. Okay, cool. Well, I'm Carson Baldus, and with Ryan Wendland, we're going to be talking about photopolymerization. Where did it come from? Where's it going? But just kind of a general overview of photopolymerization and what is a polymer. All right, so there are three main components that you should be aware of if we're talking about polymers. The monomer, that is going to be an individual unit or the building blocks of polymer chains. An oligomer is going to be a short chain of only a few linked molecules. And the polymer itself is going to be a large molecule comprised of many of those smaller molecules, usually in long chains. And this can be kind of hard to visualize. So one of my favorite analogies to use is a barrel of monkeys. So in this scenario, right, the monomer, that's going to be an individual monkey. So you have a bunch of these small units within the overall mix. An oligomer, like I said, will be a few short or a few of the monomers linked in a short chain. And then the polymer is going to be a lot more of those all linked together. However, not all of the polymers are going to be this nice straight linear structure. You might end up with some branching or different things going on. And even sometimes these chains can interconnect, and that would be what we call cross-linking, where the individual polymer chains actually chemically bond to each other, creating one giant macromolecule. However, the monkeys aren't just going to start linking arms together by themselves. That doesn't happen. You need something like an initiator that is going to be responsible for starting the reaction. In this scenario, it would be your hands, right? Because that's actually what's doing the job of linking the monkeys together and starting that chain growth. And then a resin would be the overall mix of all of the monomers and oligomers you might have, the initiator, and any other additives you might want to be incorporating in the final polymer structure. There are a couple big key classifications in terms of the different types of polymers. The first would be natural versus synthetic. So, natural polymers, things that are occurring in nature, there's quite a few of them, but things like silk, DNA even is a polypeptide, and cellulose. Those are all naturally occurring polymers you might encounter. Synthetic polymers, that's going to be more like the plastics that we're all familiar with and encounter on a daily basis. Things like rubber and silicones, and even gels. So things like your shampoo or conditioner, those are going to be, they have polymer added to them that gives them that gel, that viscous like consistency. Another big distinction between polymer types is thermoplastics versus thermosets. Thermoplastics, that's going to be polymers that are moldable when heated or able to flow. So when you heat them up, they're going to be able to be reformed and reshaped. You may have seen these types of plastic pellets before. These pellets are fully cured polymer, but then they can be melted down and reshaped into whatever other product you might want it to be, like some of those plastic bottles per se. A thermoset, that is going to be more like those cross-linked materials I mentioned before, where when it's cured, it is irreversibly hardened. So when you heat it, it might soften a little bit, but it is not going to flow, and you cannot reshape it and reform it into something else. Tires are a great example of this. They're actually so densely cross-linked that a tire is one single molecule, believe it or not, because it's so highly cross-linked. Photopolymerization, though, is a subset of polymers and polymerization in general. This is going to be light activated polymerization. So in this scenario, the starting resin has your monomer and initiator, and then you will irradiate it with high energy light, usually UV, but there's been trends towards the visible spectrum. And that initiator is going to absorb that light and get energized, and that is going to be what actually starts the reaction. One of the common mechanisms for this is going to be, a scission type where it cleaves into two radical species. Those radicals can go on to react with the monomer sites or even terminate and come together. Um, and with that, the photoinitiator over time, the light as it penetrates through the solution, that is going to be absorbed, and that's what turns into those transmitting radicals. It is important to consider how the light penetrates into the resin and things like that. Also, a fun fact, both of these pictures are not stock photos. They are actually current and former members of the Gaiman group that we've taken some of these fun photos. Just some basic industrial applications of photopolymerization. Things like surface coatings. So lots of the coatings on different materials that you encounter will be cured with photopolymerization because that liquid resin can be easily applied to an object, and then you just blast it with light and it becomes a solid cured coating. You might also see things like surface modification. So you could say add functionality to a surface where now it has different reactive sites on it it previously had. That's done using similar photopolymerization principles. Um, and even sometimes things like creating hydrogels with dual networks, but that is a little bit more complex. One of my favorite industrial applications to show is just doing floor coatings that because it's a nice liquid that the monomer resin is, you can pour it over the floor. It'll even itself out so it's perfectly level. And then you can go over top of it with something like this to cure it and harden it right in place.
All right, some other applications of photopolymerization have been used before is a lot of dental applications. So if you've ever went to the dentist and they stuck a light in your mouth and turned it on, and you're like, "What the heck is going on?" That's a photopolymerization reaction. The kind of main advantage of this is that only when the light is turned on is that resin going to cure. And so that gives the dentist a little bit more time to, say, shape a filling or fill a crack in your tooth without having to worry about a thermally cured system that has like a set time that they have to be working against. So they can go through and make sure it's perfect before polymerizing it. More dental applications, you can use kind of custom um, scanning of your mouth and teeth to form either braces or these Invisalign things or surgical guides. And so you can get exact patient specific fits and then go through and polymerize these molds to use later. And then even more, um, there are now some materials that can be used for even dentures. And so you can get kind of a scan of the mouth and make sure it's fit and patient specific, and then use different materials to polymerize, say, the kind of gum portion, which would be a little bit more soft, or the tooth surface, which would be hard to withstand all of your chewing, I guess. Some other applications of photopolymerization that we use in the Worthington lab is to make cell scaffolds for tissue engineering. And so rather than, or I guess one example of this is using thin film photomasks. And so you can see on the left of the screen, we have like this mold setup where in the top we have a photomask, which is a glass slide with different chromium dots on it, which block light in certain regions. And then if we put our pre-polymer solution or resin underneath the slide and then shine the light on it, those areas where the light isn't able to pass isn't going to polymerize and generate your solid film, which leaves you with kind of a 2.5D structure, so to say, where you still have some height, but it's a fairly thin film, and you're able to get this architecture that can then impact cell seeding, cell viability, and different applications of tissue engineering. And so just kind of get a sense of the size of these scaffolds. They're fairly small, roughly 5 to 8 millimeters in diameter and only 50 microns tall. And so they're about the size of one of these push pins, and you can also see it being ejected into your eye using a surgical tool in a mock surgical transplantation. And then at the bottom, we can also, oops, go back 1 sec. Thanks. At the bottom, we can also get into some really high resolution photopolymerization using a technique called two photon polymerization. which allows us to polymerize the structure at a very precise nanoscale precision and really get at different aspects of these retinal scaffolds with vertical and horizontal pores to allow nutrient transport.
So one of the cool applications of photopolymerization that the Gaiman group has been working on for a long time is creating zwitterionic hydrogels, meaning that they have charge on the surface, and using those to coat cochlear implants. So the implant that will go into your ear to help replace your cochlea for hearing loss, usually when it's implanted, the foreign body response will result in proteins absorbing to the surface and then corresponding cells adhering to those proteins, creating fibrosis and scar tissue around and defeating a lot of the purpose of the implant itself. So the work of the group has been on creating a coating that will go on the implant where that charge on the surface creates a water layer that actually protects the implant from having the proteins absorbing, therefore decreasing the foreign body response and allowing the implant to function as intended. This picture here, I think, is pretty fantastic in that it actually shows exactly that being accomplished, where that dark purpley tissue with the yellow dotted line around it, that is that fibrotic capsule, the scar tissue that is being generated around the uncoated PDMS from the implant. And then in the area where the coating was applied, you can see that the fibrotic capsule was actually not even able to adhere to the surface, allowing fresh new tissue to grow above and allowing the implant to function as intended.
And then maybe kind of a buzzword in manufacturing these days is 3D printing. Photopolymerization is also applicable in the 3D printing space, mainly through light-based printing options. And so there's a few different technologies out there. They all use the same principle of shining lights on your resin to generate a solid structure. But there's a few different ways you can go about it. You can use SLA to use a laser beam to then selectively cure different parts, or you can use different projectors, like a projector or even an LCD screen. And these would polymerize essentially layer by layer. And so you cure a small layer at a time, and then your build platform moves up. Your resin is able to fill in that space that was left, and then you cure your second layer and third, and so on. And so you can get these precise three-dimensional structures through light-based 3D printing. And one of the advantages of this is perhaps as opposed to other types of 3D printing is that all of the layers are chemically bonded to each other. So instead of like fused deposition 3D printing with like the filaments and melting the polymers, you have some limits in the resolution based on your filament size and heating, and these parts aren't necessarily watertight. Whereas with light-based 3D printing, you have um, better attachment between layers. It's still not perfect, but you're able to get these precise parts. And so they're being used for more and more applications in manufacturing areas.
All right. Well, it looks like we're just about out of time, so probably not a ton of time for questions. But if you have any, feel free to reach out.